All right, let's take roll. Okay, Anwar Afra is here. Anwar Afreen is here. Barner,
Here.
Davis, Hernandez, Inman, Jernigan is here. Nelson, I don't see Nelson. Osorio, Fan is here. Pilgrim is here. Ranley, Talon is here. Excuse me. Wilbert is here. And Zaradka is here. All right. So what I was thinking of doing today is going over some problems or most of the problems in assignment 5. So what I'm going to do is hand out this assignment to you guys here. I keep, oh, what do you mean?
I already printed it.
Oh, okay. Oh, shoot, this is, I have two stuff mixed up here. And for you guys, for you guys out there in Zoom, I'm going to well, I guess it's published already since some of you guys here have already printed copies. So you guys should be able to access it from Canvas. Okay, so let me share my screen. Let me go here. Let me go here. Let me go here. Files. And assignment 5. Okay, so I did publish it already. Okay, so question 1 is pretty simple. It's all a matter of converting from one unit of pressure to another. So maybe I'll do 1 or 2 of these now. So for the first one, you're going from atmospheres to torr. So to do that, we're going to start with the given value in atmospheres, which is 0.357 atmospheres. And the relationship between the atmosphere unit and the torr unit is 1 atmosphere is equal to 760 torr. All right. So that's the definition of the atmosphere unit in relation to the torr unit. So it's all a matter of doing the calculation here. So that's 0.357 multiplied by 760. And according to my calculation, this works out to be equal to 271 torr. All right. So that's basically how that is done. Okay. So now in the case of B, it's a reverse. They gave you 6.60 times 10 to the minus 2 torr, and they wanted to convert it to atmosphere. So you're going to flip this particular conversion factor to get 1 atmosphere above and 760 torr below. So let's see what that gives. 6.6 times 10 to the minus 2 times, or divided by, I should say, 760. And according to my calculation, this works out to be equal to 8.68 times 10 to the minus 5, and atmosphere would be the units of that. So that's how you do that, all right? So if you understood those two, you should be able to do the other two, C and D, in question number 1. So I'm going to leave you to do those on your own. Again, if you have any problems doing any of these problems, let me know. You have a question?
The conversion rate for torr to pascals, it's 760 torr for 101.325 kilopascals.
760 torr is equal to 101.325 pascals. And you don't have to memorize these because these will be available for you. All right, but to answer your question, that's it. Yeah. Okay. All right, so let me clear this now and scroll down. Okay, now we did some examples in class similar to what we have here, right? So let's read the question. The question says, if the atmospheric pressure is 0.975 atmospheres, what is the pressure of the gas in the enclosed gas in the left arm of the tube in each of the cases below? So what they're saying is that in each of these cases, you have the gas being trapped in the left side of the tube where it's enclosed, all right? Now, in this case here, this end is sealed, all right? So that's closed, which means that here you have a vacuum, all right? So, to answer the question, what is the pressure of the gas here? The answer is very simple. The pressure of the gas here would be 45 millimeters of mercury. And the reason why is because there's a vacuum here. The gas is exerting a pressure right here, and the height difference between here and here, between the two mercury levels on either side, is H. And according to the question, H is equal to 45 millimeters, right? So therefore, whatever the pressure that is exerted by the column of gas at this point would be the same as the pressure of the gas exerted at the same level. So therefore, this would be the answer, 45 millimeters mercury. Yes, sir.
Now, for the open end, how does that work?
Okay, so we're going to get to that. But first, are we clear on the first one? Any questions about the first one? Okay, now to answer your question, let's look at the next one right here. Now here it says that the height or the difference in the height levels on both sides is 78 millimeters, right? The gas here will be exerting its pressure here. But because this is open, you're going to have the barometric pressure being exerted here, right? And if you recall from the example that we looked at, we can say, based on this arrangement, that the pressure of the gas, will be equal to the barometric pressure plus the height of the mercury column, all right? Now, the thing is, they gave you the pressure of the gas in atmospheres. You have to make sure, in order for you to use this equation here, you have to make sure that all the units or all the pressure units are the same. Now, what that means is that we have to convert the barometric pressure, which is 0.975 atmospheres. I'm sorry, 0.9. Let me erase this here, sorry. .975 atmospheres. We have to convert that to millimeters mercury, and that would be 1 atmosphere below, 760 millimeters mercury above. So let's see what that gives. 0.975 times 760. And according to my calculation, this works out to be equal to 741 millimeters mercury. So that means that when we're calculating the pressure of the gas in this case, that would be equal to 741 millimeters mercury plus H, which is 78 millimeters mercury. And let's see what that gives. So 741 plus 78. So that gives, according to my calculation, 819 millimeters mercury. All right? So that's how that works out in the case of the middle manometer. Any questions about this one? Any questions? Okay, now in the case of the third one, again, you're going to have your gas here, exerting pressure here, but this time the height level of the mercury on this side is higher than this side, again by h, right? So therefore, and also, just as in this case here, because this is open, the barometric pressure will be acting here on the surface of the mercury, which is exposed to the atmosphere. So the relationship between the pressure of the gas here and P bar and H is P bar, the barometric pressure, is equal to P gas plus H. All right? So to find the pressure of the gas, that will be equal to P bar minus H. So P bar we already calculated here. That is 741 millimeters mercury minus H, which is 67 millimeters mercury. So let's see what that gives. So according to my calculation, that works out to be equal to 674 millimeters mercury. And that's how that works out, right? Any questions? Okay, I'm going to clear this and scroll down to number 3. So number 3 says, what is the pressure of a gas if you compress the gas from its original 500 mil at 3.4 torr to a volume of 302 mils? Excuse me. So my question to you is, what law comes to mind when you see this question? The question gave you the initial volume. So I'm going to call this P1. The initial, V1. The initial pressure would be P1, and the final volume would be V2. And the question is asking for the final pressure, so it's asking for P2. So there's one law which relates the pressure to the volume of a gas. What law is that?
Boyle's law.
Boyle's law.
Mhm.
And what does Boyle's law says?
Pressure and volume are inversely or
Proportional to each other.
proportional to each other.
Yeah, and it can also be expressed mathematically as P1 V1.
Equals P2 V2.
Exactly. Now the question is asking for P2, so therefore we'd have to rearrange this equation to get P2 is equal to P1 V1 over V2. And then what we have to do now is plug the numbers in.
For Boyle's law, we can use any units, right?
Yeah, but the units have to be the same for
Right.
P1 and P2 and V1 and V2, which is the case here, at least for volume. So P1 is 3.4 torr times V1, which is 500 mils, divided by V2, which is 302 mils. So let's see what that gives. 3.4 times 500, and then we divide that by 302. And according to my calculation, when rounded off to 2 sig-figs, the answer becomes 5.6 milliliters. No, I'm sorry, torr, because the milliliter units will cancel out. And that's it as far as number 3 is concerned, all right? So as he correctly said, when you're using Boyle's law, it doesn't matter what the pressure units are, and it doesn't matter what the volume units are, as long as they're the same for P1 and P2, and V1 and V2, all right? Okay, any questions about this one? Okay, let's look at number 4. Number 4 says, at what temperature will a gas be if you allow it to expand from the original 456 milliliters at 65 degrees Celsius to 3.4 liters. So it gives you the initial volume, it gives you the initial temperature, it gives you the final volume, and it's asking for the final temperature. All right? So what law comes to mind when it comes to this question?
Gay-Lussac's law? P1 over
It says what?
T1, P1 over T1 equals P2 over T2.
Exactly. V1 over T1 is equal to V2 over T2.
Given the temperature in Kelvin.
And the temperature must be in Kelvin. So we had to add 273 to this. Let me see what that gives. 65 plus 273. Okay, so 338 is what I got for T1, right? Now the question is asking for T2. So how would we rearrange this to get an expression for T2?
Divide, it would be V1 over T1 times P2 or V2.
Times what?
V1 over T1 times V2. Well, then, yeah, then you get 1 over T1
Hold
or 1 over T2. So,
on. Start again.
yeah. Wait a minute.
You want to isolate T2 on one side, right?
If you multiply or
So-
divide both sides by V2, you have to.
Yeah, what I would do is
in-
cross multiply. And I would get V2 multiplied by T1 over V1. All right? And then we put the numbers in. So V2 is 3.4 liters multiplied by T1, which is 338 Kelvin. And then we divide that by V1, which is 456 mils. However, we need to add something here because we have liters here, we have milliliters here. The volume units must be the same, right? So what you can do is either convert the milliliters to liters or vice versa, right? I'm going to choose to convert milliliters to liters so that I would put 1 liter here above and 1,000 mils below, so that this will go with that, this will go with that. So the only unit remaining would be the Kelvin unit. So let's see what this gives. 3.4 times 338. And then I'm going to divide that by 456 divided by 1,000. So according to my calculation, now I have to round this off to 2 sig figs. So that would be 25,000 Kelvin. And that's how you do that. All right. Any questions about this one? Any questions? All right. So let me clear this. And let me scroll down. Okay. So in this case, number 5, they gave you the moles, they gave you the temperature, they gave you the pressure, and the question is asking for the volume. So what equation comes to mind when you see this question?
Yeah, ideal gas law.
Which says what?
PV equals nRT.
Okay, so we have to rearrange this to get V is equal to nRT over P. So this is N, this is T, which we have to convert to Kelvin, 87 plus 273. So this works out to be equal to 360 Kelvin. And this is the pressure. And the question is asking for the volume. All right. So we put the numbers in, 0.56 moles multiplied by 0.0821 liters, atmospheres over mole Kelvin. Now remember, this is a constant. That doesn't change, all right? And then we multiply that by T, which is 360 Kelvin. And then we divide all of that by the pressure. Now the pressure here is 569 torr. Now here, we have to make some conversion changes because We have the pressure unit down here expressed in torr. We have the unit here expressed in atmospheres. So what I would do is convert this to atmospheres. So you multiply by 1 atmosphere over 760 torr. And that's it as far as the setup is concerned. The moles will cancel out here and here. The Kelvin will cancel out here and here. The torrs will cancel out here and here. ATM will cancel out here and here. So you'll be left with liters as your final unit. So let's do the number crunching. 0.56 times 0.0821 times 360. And then I'm going to divide by 569 divided by 760. So the answer I got, and I need to round this off to 2 sig figs, so the answer I got is 22 liters. And that's how that is done. All right, any questions about this one? Any questions? Any questions out there in Zoom? Okay, let's look at the next question. The next question says you have a gas at the pressure of 453 millimeters mercury and a volume of 700 mils and a temperature of 25 degrees. What will the temperature of the gas be if you change the pressure to 278 millimeters mercury? So I would call this P1. I would call this V1. I would call this T1. And then T2 is what the question is asking for. And they gave you P2. All right? So the assumption would be that V doesn't change because they did not give you a V2 value. So the volume is assumed to not change. So let me ask you this. What equation comes to mind when it comes to this question? What equation comes to mind when it comes to this question? I'm sorry?
Is it just like the pressure over temperature one?
Okay, so you're saying P1 over T1 is equal to P2 over T2. I would agree with that. If you look at the combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. As she correctly said, the volume doesn't change, so you can cancel out these two, right? V1 will be equal to V2. So therefore, you're left with this, right? Now, the question is asking for T2. So we have to do some rearrangement here. T2 would be equal to P2 times T1 over P1. And then we put the numbers in. So P2 is 569 millimeters mercury times T1, which is 360 Kelvin, and all divided by P1. Oh, my bad. Hold on. I'm looking at the top question. We did not convert that to Kelvin. So when you add 273 to this, that becomes 298 Kelvin, right? So that's what I need here, 298 Kelvin, all right? And then I divide by P1. Oh, I used the wrong number here too, my bad. This should not be 569, that should be 453. Okay, so this should be 453 millimeters mercury. And down here now, no. That should be 278 millimeters mercury. That's P2. Okay, so 278 millimeters mercury times 298 divided by the 453 millimeters mercury. That's the correct arrangement. All right, so let's see what this gives. 278 times 298, and then divide by 453. And according to my calculation here, rounded off to 3 sig figs, that should be 183 Kelvin. because the millimeter mercury units will cancel out there and there. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so is it okay for me to clear this? Going once, going twice. All right, let me clear this. And let's move on to question number 7. Okay, so this question is asking for you to do some calculations. The first of which is calculate the density of SO3, and it gives you the pressure and it gives you the temperature. Now, there's an equation which I derived in class, which allows you to calculate the density of a gas. Can anyone tell me what that equation is? Feel free to look in your notes, because I remember covering it, right?
MP
I'm sorry?
over RT.
Nope, we're talking about the density. The equation which allows us to calculate the density of a gas. So D is equal to what?
Is it PM over RT?
Exactly, PM over RT. And just to remind you of what these terms mean, P is the pressure, uppercase M is the molar mass, T is the temperature in Kelvin, and R, of course, is the molar gas constant. So, to calculate the density in this case, we're going to take the 0.96 atmospheres, which is the pressure, multiplied by the molar mass. So we have to determine the molar mass, and I'm going to use my molar mass calculator. For SO3, so that's 80.06. So you're going to multiply by 80.06 grams per mole. And then you're going to divide all of that by R, which is 0.0821 liters atmospheres over mole Kelvin. Multiply by the temperature. What was the temperature? Let me see here.
35.
35 degrees. So we have to convert that to Kelvin. Oops, sorry, wrong. So 35 plus 273 gives you 308. That goes here. And that's it in terms of the setup. Atmospheres cancel, moles cancel, Kelvin cancel. So the final units would be grams over liters. So 0.96 times 80.06 divided by 0.0821 divided by 308. And according to my calculation, rounded off to two sig figs, that would be 3.0 grams per liter. All right? Any questions about this? Any questions? Okay, what about B? This time, B is asking for the density of SO3 at STP. You remember what STP means, right? Standard temperature and pressure. Just to remind you, standard temperature and pressure is, well, the temperature is 273 Kelvin, and the pressure is 1.00 atmospheres, right? That's what we mean by STP. So, any ideas as to how to tackle this one? To calculate the density?
I mean, we have M, we have P, we have T, or yeah,
Mm-hmm.
and R. So just plug it in the same way.
Okay, so 1.00 atmospheres for the pressure, multiplied by the molar mass, which is 80.06 grams per mole, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 273 Kelvin. So let's see what that gives. 80.06 divided by 0.0821 divided by 273. Okay, so 3.57 is the answer I got, and the units here again will be grams per liter. But believe it or not, there's a much easier way to do this problem. Much easier way, right? And it has to do with the fact that because the question says that the conditions are STP, that means that for 1 mole of a gas, the volume would be of a certain value, which is what? What's the volume occupied by 1 mole of a gas under STP conditions? We talked about that in lecture. 22.4 liters.
Yeah.
Right, that's the molar volume of a gas under STP conditions. So if you know what the molar mass is, and if you know what the molar volume is, to get the density, all you have to do is divide the molar mass by the molar volume. So the molar mass is 80.06 grams per mole, and the molar volume is 22.4 liters per mole. So that would give you the same answer, which is 3.57 grams per liter, right? So that's a shorter way of doing that problem. All right? Okay, any questions about this one? Any questions? Any questions? All right, so let me clear this and scroll down. Okay, now this question is asking for the molar mass of a gas if its density is 3.67 grams per liter. It gives you the temperature and it gives you the pressure as well. So how would you tackle this problem?
Solve for M.
Okay, so you're using the same formula as
DRT.
above.
So it's DRT over P.
Right, so basically the molar mass based on that would be DRT over P. So the density is given 3.67 grams per liter multiplied by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 288 Kelvin. And then we divide all of that by the pressure, which is 825 torr. But again, we have to convert the torr value to atmospheres. So we're going to multiply by 1 atmosphere over 760 torr. So the torr units will cancel out, the atmosphere units will cancel out, the Kelvin units will cancel out, the liters unit will cancel out. So you're left with grams per mole in your final answer. So 3.67 times 0.0821 times 288, and then we divide by 825 divided by 760. And according to my calculation, when rounded off to 3 sig figs, the answer is 79.9 grams per mole. And that's how that is done. All right? Okay. Any questions about that one? Any questions? Any questions?
Is it 760 or 260 for the?
760. 760 torr is equal to 1 atmosphere. Okay, any other questions? Any other questions? All right. D. Now, in the case of D, they're asking for you to calculate the molar mass again, but this time it doesn't give you the density. It gives you the mass in grams, and it gives you the volume in liters. So you can use those two to get the density, right? They also gave you the pressure in torr and the temperature in Celsius. So basically, you're going to use the same equation here, but this time, where you have density, you're going to put this divided by that, right? So it's going to be 4.40 grams divided by 3.50 liters. So this here would give you the density, D. You're going to multiply that by 0.0821 liters atmospheres over mole Kelvin. And then we're going to multiply by the temperature, which is 41 plus 273. So you're going to multiply by, oh shoot, what's happening here? You're going to multiply by 314 Kelvin, and then you're going to divide all of that by the pressure, which is 560 torr, but you have to convert to atmospheres again. So 1 atmosphere over 760 torr. So the torr units cancel, the atmosphere units cancel, the Kelvin units cancel, the liter units cancel. So again, your answer will be expressed in terms of grams per mole. So it's a matter of just doing the number crunching. 4.40 divided by 3.50 times 0.0821 times 314. And then I'm going to divide by 560 divided by 1,000. Okay, so according to my calculation, how many sig figs? 2 sig figs. So I got 58 grams, 58 grams per mole. 58 grams per mole is what I got. All right. Let me do it again just to make sure. 4.40 divided by 3.5 times 0.0821 times 314 divided by. Okay, I got something different now. Okay, let me do this one more time. 4.4 divided by 3.5 times 0.0821 times 314 divided by 560 divided by 760. Okay, I got a different answer, so I think this one is incorrect. The answer I got is rounded out to 2 sig figs, 44. Okay, so that's basically how that is done. Any questions about this one? Any questions? Any questions?
Why are we rounding to 2 sig figs?
Because of the 560 right here. That's 2 sig figs.
Gotcha. Yep, that's right.
All right. Okay, any other questions? Any other questions? Okay, so let me clear this.
Wait, why is the 562 sig figs?
Because there's no decimal place or decimal points in that number. So the 0 is not significant.
Oh, okay.
You see what I'm saying? If there was a decimal point here, then that 0 would be significant, and therefore that would be 3 significant digits represented.
Okay.
Okay, so let me clear this and scroll down. Okay, so this one says you have to calculate the partial pressure of each component in a mixture of gases, and it gives you the numbers in terms of the mass of each gas. It gives you also the temperature, it gives you the volume of the mixture, which is 1 liter. All right? It's actually very simple, a bit long-winded, but it's very simple. Basically, what you need to do is calculate, using the ideal gas equation, the pressure of each gas, right? Now, there was one equation which we derived in class, which was uppercase M is equal to MRT over PV, right? Now, just to remind you what each of these terms mean, uppercase M would be the molar mass, lowercase m would be the mass in grams, R is going to be the molar gas constant, T is the temperature in Kelvin, P is the pressure in atmospheres, and V is the volume in liters. Now, in this particular case, the question is asking for the pressure of each gas. So I can rearrange this to solve for P, which is equal to MRT over uppercase MV. And basically, this is the equation that you're going to apply to each of the gases presented in this question. So if I were to calculate the pressure of nitrogen, that would be equal to the mass of the nitrogen given, which is 3.50 grams, times R, which is 0.0821 liters atmospheres, over mole Kelvin, times the temperature. The temperature is 25 degrees, which is the same thing as 298 Kelvin. So that goes here, right? And then we divide all of that by the molar mass. What's the molar mass? Well, for nitrogen, that would be 14.01 times 2. So that's going to be 28.02 grams per mole. And then we multiply by the volume, which is 1.00 liters. And that's basically the setup. The liters will cancel out. The mole will cancel out. The kelvins will cancel out. And the grams will cancel out. So the only unit remaining would be the atmosphere unit. So let's do the number crunching. 3.5 times 0.0821 times 298. And then I'm going to divide that by 28.02 divided by 1. So I got, and please correct me if I'm wrong, but I got 3.06 atmospheres. That's what I got. All right? And basically, it's the same calculation for the other gases. Let me just draw a line right here. The next gas is hydrogen. So it's the same equation. The numbers are going to be a bit different because in the case of hydrogen, the mass is 2.15 grams multiplied by R, which is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is again 298 Kelvin, and then divided by the volume, divided by the molar mass. Now for hydrogen, that's 2 times 1.008. So that's 2.016 grams per mole, multiplied by the volume, which is 1.00 liters. And that's it. So let's do this. 2.15 times 0.0821 times 298. And then I'm going to divide that by 2.016 times 1. And according to my calculation, this works out to be equal to 26, how many sig figs? 3 sig figs. So 26.1 atmospheres. That's what I got. All right. Okay, any questions about this one? Any questions? Okay, and the next gas is ammonia, right?
Are we,
Oh, I'm sorry, what's that?
so for hydrogen, you used 1.008 for
Wait,
the molar
no,
mass?
it's H2, so you have to multiply by 2.
Right, so, but you used 1.008.
0.08, right.
Okay,
Yeah. Okay, so in the case of ammonia, I'm going to be lazy here. I'm going to erase this here, and erase this here. And since we're working with ammonia, in this case, I'm going to put NH3 here. Here, I'm going to put the mass of ammonia, which is given as 5.27 grams. And then down here, I'm going to put the molar mass of ammonia, which is, okay, let me do a quick calculation here. 3 times 1.008, and then plus 14.01. Okay, so in the case of ammonia, the molar mass is 17.03 grams per mole. So that's the setup. Let me erase this here. So let's do the calculation. 5.27 multiplied by 0.0821 multiplied by 298 divided by 17.03 times 1. Oh gosh, I did something wrong. Okay, let me do a second. 5.27 times 0.0821 times 298 divided by 17.03 times. Okay, so according to my calculation again, the answer here works out to be equal to 7.57, and the units again would be atmospheres, right? And that's it. That's number 8. Any questions about number 8? Any questions? Okay, let me clear this. And scroll down to number 9. Okay, now number 9 is a very interesting question. Number 9, it talks about the fact that you have 4 containers, right? So according to this question, Okay, according to this question, container A has a volume of 1.23 decimeter cube, and the pressure of the gas in that container is 3.24 atmospheres. In the case of container B, the volume is 0.93 decimeters cube, and the pressure of that gas is 2.82 atmospheres. In container C, the volume is 1.42 decimeter cube, and the pressure of that gas is 1.21 atmospheres. And then the question says, if all these gases are put into container D, and the volume of that container is 1.51 decimeters cube, what is the pressure in container D? All right. Now, this question basically will require the use of two laws. Now, can anybody tell me what those two laws are? There are two laws that you'd have to use in order to solve this problem. One has to do with the relationship between pressure and volume, and the other has to do with mixtures of gases.
Is one Boyle's law?
Boyle's law is that law which deals with the relationship between pressure and volume. What's the other law? There's a law that deals with gaseous mixture. Dalton's law of partial pressures, right? So those are the two laws which will come into play in this problem. So how are we going to tackle this problem? Well, what we should do is find out for each gas, what would be the pressure when each of these gases are put into container D, right? So basically, Boyle's law says P1 V1 is equal to P2 V2, right? So basically, we need to find P2, which is P1 V1 over V2. So we're going to do a calculation here for A. For gas A, P2, when it's transferred into this container D, I'm sorry, P2 is going to be equal to P1, for which the value of P1 in that case would be 3.24 atmospheres times V1, which is 1.23 decimeters cube, divided by V2. What's V2? The final volume, which is 1.51 decimeters cube. All right? So let's see what that gives. So that's 3.24 times 1.23, and then divide that by 1.51. And according to my calculation, this works out to be equal to 2.64 atmospheres. All right, because the decimeter cube units will cancel. So that would be the pressure exerted by gas A when it finds itself into container D. So let's do for gas B. What would P2 be equal to in the case of gas B?
P2 is equal to 0.93
0.93 decimeters cube
times 2.8
times 2.82 atmospheres
over
over
1.51
1.51
decimeters.
decimeters cube. Exactly. So let's see what that gives. 0.93 times 2.82, and then divide by 1.51. And according to my calculation, this works out to be equal to 1.74. Okay, what about gas C? For gas C, what would P2 be equal to?
1.42 decimeters cubed.
1.42 decimeters cube
21 ATM divided.
times 1.21 atmospheres divided by 1.51 decimeters cube. And let's see what that gives. So 1.42 times 1.21, and then divide by 1.51. And according to my calculation, this works out to be equal to 1.14 atmospheres. All right. So we're not finished yet because the question is asking for the pressure of all the gases in that same container D, right? So how do we find the total pressure?
Just add them all up.
Add them up. At 2.64 atmospheres plus 1.74 atmospheres plus 1.14 atmospheres, and that's it. So let's see here. 2.64 plus 1.74 plus 1.14. And according to my calculation, this works out to be equal to 2.52. I'm sorry, 5.52 atmospheres. And that's how that is done. All right. Any questions about this one? Any questions? Okay, moving along. Let's clear this. Scroll down. Okay. Now, this question says, a mixture of gases is made by connecting a 7.50 liter flask containing nitrogen to a 2.0 atmosphere. I'm sorry, containing nitrogen at 2.0 atmosphere to a 13.0 liter flask containing hydrogen at 1.00 atmospheres. Okay, now, I don't know about you guys, but a question like this, I like to draw a diagram which gives me a visual as to what we're talking about here. So let me do that here. So you have two flasks that are connected to each other. You have this flask here, and please forgive my poor artistic skills. I'm not good at drawing at all. All right, so let's say you have something here separating the two, right? And so let's say this is the one that contains nitrogen, and this is the one that contains hydrogen, all right? And according to the question, the volume here is 7.50 liters, and the pressure is 2.00 atmospheres, right? And then for hydrogen, the volume is 13.0 liters, and the pressure is 1.0 atmospheres, all right? So the question is asking in A part, what is the final volume of each flask, right? So basically what that means is that you're going to open up the stopcock here. Whoops, sorry. So basically all the gases will flow throughout the entire container, right? 1 minute here. Okay, so basically you're going to have total mixing of the nitrogen and hydrogen between the two flasks, right? So the question is asking, in the A part, what is the final volume of each gas? And the answer is what? What do you think?
20.5.
I'm sorry?
20.5.
Repeat that?
20.5.
Okay, how did you get that? Adding the volumes, 7.50 liters plus the 13.0 liters, and that will give you 20.5 liters. Okay, very good. So the next question is, what is the partial pressure of each gas? Now, the assumption is they're talking about the partial pressure of each gas upon mixing, right? Let me get rid of this here. Okay. Okay, I'm not sure why that won't cooperate. Anyway, so how will you get the partial pressure of each gas after mixing? What law comes into mind?
Use Dalton's law and add them together.
Nope. We're not adding them together yet.
It's the partial pressure of each gas.
Right.
Wouldn't you just calculate? Well, partial pressure of each gas. Would that just be the individual pressure across the entire volume?
Yeah, but how do you get that? Across the entire apparatus.
Their individual pressures. So it,
Mhm.
for nitrogen, it would be 2 ATM.
Well, for nitrogen, it was 2 ATM, but when it mixes, the pressure will change.
Right. So oh my gosh.
So what law comes into mind?
Oh, wait, it's going to be the pressure volume. So
Exactly, Boyle's law,
Boils, yeah.
right? Because you have the initial pressure of each gas, you have the initial volume of each gas, and you have the final volume of each gas, which will be the same for both gases because both gases occupy the same volume in the apparatus. So let's focus on the nitrogen, right? So P2 for nitrogen would be equal to what? what would be well, P2, let me write this general formula here. P2 is equal to P1 V1 over V2, right? So in the case of nitrogen, for nitrogen, right? What would be P1? 2.00 atmospheres, right? What would be V1?
7.5.
7.50 liters, exactly. And then what would be V2?
20.5.
20.5 liters. And that's it. So let's see what this gives. 2 times 7.5 equals divided by 20.5. So according to my calculation, this works out to be 0.732. 3 sig figs. Atmospheres, all right? So that's for nitrogen. And then what would be the pressure for hydrogen? P2.
It's going to be
What's P1 for hydrogen?
1.00.
1.00 atmospheres. What's
13.
V1 is 13.00 liters. And then, I'm sorry, 13.0. Hold on. I want to get the sig figs right.
13.0 liters.
Oh, it's 13.0.
Yes.
So I added an extra 0 here, which I didn't need to. Okay, so 13.0 liters, right? Divided by V2, which is what?
20.5.
20.5 liters, exactly. So let's work that out. So that's 2.5. Okay, so according to my calculations, this works out to be equal to 0.634 atmospheres. All right? So that's the answer for B, because B is asking for the partial pressure of each gas. All right? And then now, in the case of C, they're asking for the total pressure, right? And we all know how to do that, right? What is the total pressure?
Add the two together, you get 1.366 ATM.
Total pressure is equal to 0.732 atmospheres plus 0.634 atmospheres. And let's see what that gives. 0.732 plus 0.634. So this works out to be 1.366 atmospheres. And that's it. All right. Any questions about this one? Any questions? Any questions? All righty. So let's clear this and see what's below that. Okay, now this one has to do with the situation of collecting oxygen, or for that matter, gases over water, right? And if you remember, the way the experiment is set up, it's set up such that you have the jar, which is filled with water, which is inverted into a trough filled with water, and then you have a hose leading the gas from wherever it is generated into that bottle, and then the gas is basically collected over water. As the amount of gas increases, it forces down the water level. And what we try to do is make sure that the water level inside the flask is the same as outside the flask, because when that happens, that means that the barometric pressure, P bar, would be equal to the total pressure of the gaseous mixture, which would be equal to the pressure of the gas plus water vapor pressure, right? So in this particular question, they gave you the volume of oxygen that's calculated. They gave you the barometric pressure, P bar, and they gave you the temperature of the water. And the question is asking how many grams of oxygen were collected. And it gives you an important additional information. It gives you that the vapor pressure, this should be the vapor pressure of H2O, is 19.8 millimeters mercury, right? So that's this right here, right? So firstly, we can find the pressure of the gas easily because they gave us the barometric pressure and they gave us the vapor pressure of water. So, I mean, yes, they gave us the vapor pressure of water. So therefore, the pressure of the gas would simply be equal to the barometric pressure minus the vapor pressure of H2O. So the barometric pressure is 762 millimeters mercury, and the vapor pressure of water is 19.8 millimeters mercury. So let's see what that gives. 762 minus 19.8, and that gives 742 torr as the pressure of the gas. Now, remember, the question is asking for the mass of the gas in grams. So if you remember, the PV is equal to nRT equation. Oh, no, not that equation. I'm sorry. The equation for molar mass. M, uppercase M is equal to lowercase m RT over PV, right? The question is asking for M. So we can rearrange this equation to get uppercase M PV divided by RT. So let's put the numbers in. The molar mass of oxygen is going to be 32.00 grams per mole. Sorry. Ah. 32.00 grams per mole times the pressure. Now, what's the pressure? We just calculated it here, 742 torr, but we have to convert that to atmospheres. 1 atmosphere over 760 torr, that's what we multiply by, and then we multiply by the volume. What's the volume? 193 milliliters, which we have to convert to liters, so that would be 0.193 liters. And then we divide all of that by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 22 degrees. So 22 plus 273, that gives you 295 Kelvin. So that's the setup. So it's all a matter of doing the number crunching. Running out of space here, so let me erase this top part here. Okay, so let's see what is the result. 32 times 742 divided by 760 times 0.193, and then divided by 0.0821, divided by 295. And according to my calculation, I'm just going to write the answer up here. The answer I got is 0. How many sig figs? 3 sig figs. So 0.249 grams is the answer. I'm running out of juice in my battery.
What did you use as the trying to think of what I'm trying, molar mass for the oxygen? Is that 32.00 grams?
Yeah, 32.00. Because oxygen, remember, is one of those elements that exist as a diatomic, right? So for one atom, it's 16.00. So for two, it's 32.00 grams per mole. All right. Okay. Any other questions about this one? Any other questions? Any other questions? Okay. So let's clear this. And let's see what's next. This is, I think, going to be O. Okay, you know what? I'm going to stop here because this question is a bit involved. But you can try it on your own. In fact, you can try the rest of the assignment on your own. Today's what? Today's Wednesday. Okay, so I guess we can continue this discussion on Friday. Before you leave, let me just say that the test is scheduled for next week, Friday, but I've been reminded of a meeting that I have to attend in Jacksonville. I'm sorry, not Jacksonville, Daytona. So I won't be here on Friday. So basically that means that I'll have to put off the test until next week this time. next Wednesday. All right?
So 2 weeks from now?
No,
Oh, 1 week from now.
exactly.
You're just gonna move it.
Because, right,
To the 15th.
uh, yeah, so you're right, 2 weeks. I mean, yeah, 1 week, right. Yeah,
We lose.
hold on, maybe I misspoke. Hold on, what did I say?
1 week. You said it was originally going to be the 17th.
17, so, oh, right, so I was thinking that, actually put it off until 2 weeks, actually, because
They're doing the 22nd.
the 22nd, yeah. Yeah, so that's that, so just to let you know. All right, so that's pretty much it, folks. Try the other questions in the assignment, and we can come and discuss it next class, all right? Okay, I have a meeting right now, actually. Oh my goodness. Okay, let me see here. Somebody asked a question, do we need to memorize formulas for the test? Okay, I guess it depends on what formulas. If you're talking about the gas laws, some of them you need to memorize, some of them are provided in the handout. So that's pretty much the best answer I can give you. All right. I'm going to sign off now because I have to attend another meeting in the next 2 minutes. All right. So I'll see you guys.